Sorry, everyone.
Just an empty screen right now.
Okay, can you see it now?
At the very top, but it's somehow off.
So let me try that again. So,
I mean, this is visible. It's only if you switch to full screen that it.
Can you see it full screen now?
No, I can see your presentation software. Like I can see the slides, but not in full screen. I can see your software.
What about
now? Perfect.
Right.
Perfect.
Right. Sorry about this.
Now
I can hear feedback, I think. So anyway, okay. So thanks, Paulina, for the introduction. Sorry for this little technical problem. Very happy to be here today. Along with Richard, we're going to tell you about how to do deep learning for EEG using PyTorch and MNE-Python. And so I wanted to start the tutorial with a little presentation, should it be longer than 15 minutes, just to give you some background on both the sleep staging task that we'll be working on today, and also give you a brief overview or a refresher on deep learning. I'm not sure what kind of background everyone has here today. So of course, I won't be able to go in much depth, but hopefully I'll give you some pointers, or you'll be able to connect the dots later on based on that. And then finally, we'll talk about the notebook that we'll go through. So if you have any of this background, this will help you today. So any basic knowledge of EEG, if you've done scientific programming in Python, NumPy, Matplotlib, Pandas, etc., MNE-Python, of course. And then finally, basic concepts of machine learning, such as what Alex has just talked about earlier today. So all of the material is already available if you want to take a look, but we'll get back to it in a few minutes, and we'll post the link in the chat. So first part, introduction to sleep staging. So if any of you are in neuroscience or psychology or related fields, you might know that the EEG during sleep is actually pretty wild. There's a lot of stuff that happens while we sleep in the EEG with very distinct patterns, very strong transient events that appear during the night. And so we typically break down sleep into 5 sleep stages. First one being wake, although it's not actual sleep, it's part of this categorization. Then we have 3 non-REM sleep stages, and one being the lightest sleep stage, where it's very easy to be woken up, and N3 being deep sleep, where it's very hard to be woken up. And finally, REM sleep, which is where most of the dreaming occurs, for instance, and is very interesting from an EEG perspective because it's very similar to wake EEG. So now I'm introducing a graph that we call a hypnogram. And a hypnogram is essentially just a plot of the sleep stage across a night recording. So here we see that we have about 8 hours of sleep time, and then we see the sleep stages across that recording. And what we see on top of these sleep stages is that there is a sleep cycle structure. So we have cycles of about 90 minutes that repeat throughout the night, and where we go from awake or light sleep all the way to REM sleep. This is what we call sleep macro structure. But there's also sleep microstructure. And by that, I mean that each stage is characterized by different frequencies and various transient events. So I won't go through the entire table here, but for instance, in stage N2, we see what we call sleep spindles. So these are oscillations at around 11, 12 hertz that occur during N2 and are very often followed by K complexes, so these sharp sawtooth waves. During N3 sleep, we have slow waves, which are these slower waves with very high amplitude. So we have both this stage structure, cycle structure, and this microstructure with events on the second to second scale. This is, in a nutshell, the EEG during sleep. So now, how is this data recorded, and specifically in a clinical setting? So in a clinical setting, you would run a test that we call a polysomnogram, and it's recorded in a well-controlled environment. So for example, in a sleep clinic, and we'll record many different sensors at once. So of course, EEG, but we might also include EOG, EMG, maybe respiration, pulse oximetry, and whatever else you want to include there. So once we we record an, for example, 8-hour long sleep recording, we need to ask sleep experts to annotate the data manually. And by manually, I mean that sleep experts use software that could look like something like this, where they see all of the raw signals that we're recording during the night for a 30-second window. And so one window by window, they look at the signals and identify patterns to finally give a label to that window. So this is a very lengthy, time-consuming process because you have to do that for very long recordings, one window at a time. And then finally, once you have these annotations, you can extract different clinical markers that can help in diagnosing different sleep disorders, for example, sleep apnea or insomnia, etc. So given that manual sleep staging is pretty time consuming, is there any way we could automate it with machine learning? And of course, the answer is yes, and that's the topic of today's tutorial. In the field of automated sleep staging, there's been many different approaches that have been tried over decades now. And most of that work was done originally in a traditional feature-based machine learning pipeline or a scenario, where starting from raw EEG data and based on expert knowledge, for example, sleep experts or engineers working on this kind of problem, you want to extract features or good descriptors of that data such that a classifier would then be able to know which sleep stage this data comes from. So we would typically start this pipeline with some preprocessing, which you've done earlier today in the M&E tutorial, and then follow up with a feature extraction step. So in the case of sleep staging, we might want to extract a power band or log power and frequency bands, knowing that they vary between the different sleep stages. And then finally, once we have all of the features we care about, we can pass them on to classifiers, such as logistic regression, which then learns the mapping between these features and the sleep stages. But then what if you're not really willing to spend the time and effort coming up with these features, and also knowing that you might not know, there might not be a known way of extracting the optimal features for this problem? Well, this is where deep learning approaches become interesting. So in a deep learning approach, instead of working on feature extraction, you'll work on designing a neural network architecture that will learn both the feature extraction step and the classifier step all at once. So a pipeline would typically look like this. You start again with preprocessing, then you design your neural network architecture. We'll talk about that in a minute. And finally, you can train your neural network. So in both cases, you end up with a function that maps a raw EEG window to a sleep stage. And if we're thinking in terms of pros and cons, well, one very obvious one is that a traditional feature-based approach is interpretable because you know the features, you've designed them, so you can try to interpret what the classifier is doing. However, this comes at the cost of extensive engineering effort. On the other hand, in deep learning, you might be able to discover optimal features for your problem. However, this comes at the cost of having many architecture and training hyperparameters to tune, and this can take quite a long time. So of course, today we're focusing on a deep learning approach to this problem of sleep staging. Main reason for this is that in the last few years, we've seen state-of-the-art approaches being designed with deep learning. All right, so part two, a brief overview of deep learning concepts. So there's three main components to define when talking about deep learning. And I'll dedicate one slide to each one of these concepts. The first one is architecture. So the architecture specifies the space of all functions that can be modeled by our network. Examples might be fully connected, convolutional layers that we'll talk about in a sec. Second component is the loss function. So the loss function is a function that measures how well your neural network performs its task. And we'll talk about mean squared error in multi-class Gross entropy. And finally, you need the learning rule, which glues the other two components together by telling you how to adapt the weights of your architecture so that you minimize your loss function. And in deep learning, this is typically done with something called stochastic gradient descent and an algorithm called backpropagation. So now let's go through each one of these components one by one. So first, for architecture, we'll actually cover two types of architecture here. So generally speaking, in a deep neural network, you have this concept of layers. So here we have 4 different layers, 2 hidden layers in the middle, and the concept of neurons or units in each layer. So each layer has a number of neurons or units, which are represented by nodes here. And in a fully connected fully connected network, each neuron is connected to every single value from the previous layer, and every single value or node, of the following layer. So that's why it's called a fully connected network. And so given an input, so here our input might be a window of 30 seconds of EEG that we've flattened into a single vector. We can pass it on to the input layer, and then each node from the first hidden layer will compute a weighted average of all of these values, and then apply a nonlinear activation function and pass this output to every neuron in the next layer. So we just need to propagate these values to the entire network until we get at the end. For example, here we have 5 output values, so you could consider that each of these output values correspond to the probability of one of the 5 classes happening. And so in a way, you can think of this as just being stacked logistic regressions. And the second type of architecture that we'll cover quickly here is a convolutional neural network, or ConvNet. So ConvNets are really at the core of many deep learning application nowadays, especially in computer vision, but also in EEG processing. And the main interesting trick behind convolutional neural networks is that they use a convolution operation, which dramatically reduces the number of weights that you need to train. And at the same time, has this nice translation invariance property, where if a pattern occurs somewhere in your input, it doesn't matter if it happens at the beginning or at the end, your network should still be able to detect it. For example, in a sleep EEG or sleep staging scenario, if you have a sleep spindle at the beginning of your 30-second window or at the end of your 30-second window, your network should still be able to say that this is N2 sleep. So in a nutshell, ConvNets rely on convolution operations that allow weight sharing and also translation invariance. So there's a bunch of other types of layers or architectures that exist and that we won't have time to cover today. So next component, the loss function. So the loss function tells us how well a neural network is performing at its task. For instance, if you're doing a regression task, you might want to use something like the mean error, where you have the prediction of your neural network that you target, and you're just trying to minimize this difference across the M examples of your data set. For a classification task, like what we're going to do today, we'll use cross-entropy loss. So the cross-entropy loss is, again, a function that you want to minimize, and where you compare the true probability of an example I for class J to the log probability predicted by your network for the same example I and class J. And then you sum this over all of the classes and all of the examples in your training set. There are other, sorry about that. There are other loss functions that one could use, but again, that we won't have time to cover today. And finally, the last component is the learning rule. So as we just saw, we want to minimize the value of our loss function. And this is what our loss function might look like in 3D. So we have this function that we don't know the exact shape of, but we know that there's a minimum, either local or global, somewhere in the function. And we want to find the right combination of parameters so that we find the smallest value of this loss function. So to do that, we need to know whether we need to increase or decrease each value of each parameter of our neural network. And how do we do that? So there's an algorithm called backpropagation, or backprop for short, which is essentially just a simple application of the chain rule to compute the derivative of the loss with respect to each parameter in your entire network. And so now that we know in what direction to push each weight, we can take a step in that direction, which is represented by this little arrow here, and then measure the loss again. Hopefully it will have decreased, and then compute the gradient again, and then apply a new step, and then go over and over. And this is what we call gradient descent. And nowadays, the backpropagation algorithm is very conveniently handled by packages such as PyTorch and TensorFlow, so you don't have to think as explicitly anymore about backprop, but it's still at the core of deep learning. So obviously, there's also a lot of concepts that I didn't have time to talk about. If you're interested, I really recommend the Deep Learning book by Ian Goodfellow, which is an amazing resource to get started in the field. So now, your mission for today, this tutorial, as you might have understood from all of this presentation, will be to train a convolutional neural network to perform sleep staging and hopefully try to improve on the performance of a default model. And so at this point, I'll let Richard introduce the Jupyter Notebook and help you set up the tutorial. If you have any questions, I'm happy maybe to answer them as they come on the Q&A or in the chat. But other than that, I'll let Richard take the lead now.
Hey there. My computer just broke and I cannot power it on. So I'm sitting here now with my phone in my hand and an iPad in front of me on which I cannot join Zoom, but we can try to work through this anyway. Okay, so Hubert has prepared a Jupyter Notebook, which is also shared on Colab. I'm not sure if that has been shared in the chat already. Is it in the chat?
I just shared it in the chat.
Yes, okay, so that's a link to a GitHub repository where you can find the tutorial to download or the notebook to download. And there is also a link which says, open this tutorial in Google Colab. This is the convenient way for you to actually, where's the link? The link is in the chat right here. Or did you send it? Hubert just sent it to the chat. Okay, okay. So yeah, okay, okay. So you got it. Okay, everybody got the link. If you cannot find the link, do speak up. Okay. So if you go to that GitHub site, there is a link which says open this tutorial in Google Colab, which is convenient to actually run this without any local installation. So if you click, I have to tap there, you probably click. If you click there, the remote processing environment called Google Colab pops up. Oh, Hubert, right. That's perfect teamwork. Yes, can you follow that link? Let's just wait for Hubert. Okay, perfect. So this is the notebook that Hubert has prepared for you. We're going to work with MNE Python and PyTorch, and we're going to use a data set which is called Fusionet or Fusionet sleep data set. So they recorded, I think, 70-something participants during sleep. They recorded EEG, and participants came in for 2 sessions or 2 nights, essentially. Now, as Hubert, since my computer broke, I missed his presentation, but I guess he explained briefly which sleep state, that there are different sleep stages. Typically, we consider there's 5 of them. 1 is wakefulness, 1 is REM sleep, and then there's 3 more which are non-REM sleep stages, from light sleep to deep sleep. And the idea here is to train a neural network to automatically and hopefully correctly classify sleep stages of EEG data. A cool thing about this PhysioNet dataset is that there have actually been experts working on it, looking at it, and they have done the classification for us. So this is perfect to feed into a neural network to train it and later test how well it performs. So we don't need to be sleep experts to get this to work. Isn't that great? Okay, so to make good use of that Colab notebook, you should click on that link at, yes, exactly, where it says copy to drive. Actually, copy to drive. No? Yes, there. This will create a copy. Is it working? Actually, I cannot see what's happening on your screen because my phone screen is so small. This will create a personal copy of that notebook in your Google Drive. And this also means that you can now modify things and they will get saved. So this is great. Next thing we want to do is we want to ensure that hopefully we have access to a machine in the Google data center that is equipped with a GPU, a graphics card, essentially. And to do that, we go to the menu, click on Runtime, and what is it? Change runtime type. Parfait. And we select GPU. I'm going to try to follow along on my iPad, but it's going to take a little bit longer. And then click OK. Now, hopefully, we ended up on the machine with a usable GPU, which will help speed up certain calculations in the process. Okay, so let's maybe briefly look over what we're going to do here. So the first steps are actually not so interesting. So we're just going to install all dependencies, meaning PyTorch, MNE, Matplotlib for visualization, pandas. So easy stuff. If we scroll through, yes, you can. I mean, you can execute that right now if you wish to, but you can also do that later. I just want to give you a brief overview, so you don't have to actually actively follow along now. Just I want to show you what's to be discovered here in the notebook. So section 1, loading data. We're actually just going to load the first 30 subjects, and for each subject, we're going to record. We're going to load one recording. I mentioned earlier there's 2 recordings per subject, and there is more subjects than 30, but we don't have enough time, especially while we're still experimenting with the neural network. So we restrict ourselves to just 30 subjects and 1 recording per subject for the time being. So all this code you're seeing here, you don't really need to dive into that because it's really just loading that PhysioNet data. So it's very specific to that particular data set. But in the end, if you can scroll a bit down, Hubert, where we see that figure. Yes. In the end, you should see a plot which looks like this. This is just a visualization of the raw data of the first data set we loaded. Unfortunately, inside this Colab notebook, it's not interactive. Normally, you would be able to scroll left and right, meaning through time, but this doesn't work here. However, what you can see already is there is this bar at the bottom, and it has different colors. And these colors, they encode for different sleep stages that were actually tagged as such by experts. So this is what I mentioned earlier. Experts have actually tagged this data set, classified this data set. And just above the figure, you can see sleep stage W. This means that the color or the current section of data we're currently looking at was classified as W is, I think, wakefulness, right? Being awake. Okay, let's move on to step number 2. We need to pre-process the data in some way. So what we would typically do with EEG data is we would apply some kind of temporal filter. Here, in this example, it's going to be a low-pass filter with a cutoff at 30 Hertz. So this seems to be good enough for the time being, and we plot the spectrogram then to see the effects of the filtering. Here we can see that the frequency or the power drops as frequency goes above 30 Hertz. So the filter was successful. But this is just to already prime you for that. This might be something you could potentially consider to alter a bit, to tune a bit, to see if and how it impacts performance. Okay, if we scroll further down, this is just code that essentially extracts so-called epochs, that is 30-second segments of the data that belong to specific sleep stages. So it would essentially slice the data, 30 seconds, 30 seconds, 30 seconds, 30 seconds, and so on and so forth, and would always use the experts tags that are part of the raw data and would attach this tag to each individual slice. So this is going to be the data essentially we're going to work with. Isn't that convenient? We're also going to scale the data. So it's going to be a standard, is it called a standard scaler? It's just a very, very simple function that ensures eventually we have a mean of 0, which helps the algorithms later to work better, to perform better. Yes, so this was really just preparations, like really just data loading and you know, bringing it in. Now, section number 3, we're going to divide the data into train, validation, and test data sets. It's 3, and I want to emphasize it's 3. It's not just training and tests, it's training, validation, and tests. So here we want to ensure that the data we eventually use as test data to test how well our network actually performs. We want to ensure that this test data has never been in touch with our classifier before during training. Okay, that's why we're producing 3 data sets, 3 splits. Okay, just trying to follow along on my iPad. Sorry, that's yeah, right. One thing we want to do is yeah, right. The test data set, as test data set, we're going to use the first recording. As I said, there's typically 2 recordings. We only use 1 anyway, but we're going to use the first recording of the first 10 subjects. That's going to be our test data set. We're going to put that aside, and we're going to take the rest of the data, and we're going to split it into training and validation. We're going to work with that. So after we've done that, we can have a look at how many actually samples of the different classes do we have. And we can see there's quite a stark imbalance. So there's lots of samples for N2 data and much fewer samples for N1 labeled data. So this could actually this imbalance could pose a problem later on. We would like to avoid running into this issue, and therefore we need to apply some weight to the data, and this is what we're going to do in the next code block. Okay, whew. That's tough. And now finally, finally, we can start to actually create a neural network. So this network is essentially based on, well, not just based on, I think it's the exact same network as was proposed in or published in this publication by, I hope I am pronouncing the name correctly, Chambon et al. In 2018. This paper is quite interesting and also helpful while you're doing the task, I guess. So I actually wanted to share with you a link to the archive preprint. However, since my computer crashed, I don't have access to that, but I will later share it to the chat. Because there they explain how they came up with that specific network and how it performs, etc. Okay, so we're trying to recreate this network. Okay, I can see the link to the paper has just been shared to the chat. So head over to the chat. Yes, so we're going to recreate this network. So there's lots of stuff going on there. And Hubert may disagree, but I would just say, for now, you don't need to understand all of what's going on there. Just take this for granted for now, because this is just a recreation of a network that was proposed in this 2018 paper. Okay, so this is a convolutional network. And now we're going to actually, in the next step, we're going to actually train the network and see how well it performs. I don't think there's too much to say here, because it's essentially a bunch of code. But the interesting stuff actually is then the output. So you get a table where you can see different performance measures, the loss. So remember, we're trying to minimize the loss as we go along, and the visualization of the learning curves. Yeah, and lastly, we want to look at, yes, please unfold and scroll down a little bit. Yes, perfect. This is what we were hoping for. A confusion matrix that actually tells us in a straightforward fashion how well the network performs when classifying sleep data, and where it makes mistakes and incorrectly labels certain data points, or certain epochs with the incorrect sleep stage. And at the very bottom, we have a hypnogram. I learned this term today. I didn't know it before, but it's quite neat. So on the x-axis, you have time. And on the y-axis, you actually have the sleep stage. It goes from wakeful over light sleep, deeper sleep, deep sleep, up to REM sleep. And the blue trace here shows how experts labeled the data, and the yellow trace, or is that yellow? Yeah, orange trace. It shows how our classifier, our network, actually classifies things. Yes, so up until that point, you wouldn't even have to touch much of anything except for the run button. Because all the code you're going to need to generate what you saw here is already there. However, of course, it wouldn't be of advantage to actually play a bit with that stuff. So you may, for example, be interested in looking into different effects of preprocessing on the classification performance. So, for example, here we only applied a 30 Hertz low-pass filter. What is going to happen if you apply a, let's say, 10 Hertz low-pass filter, or if you apply a band-pass filter, 5 Hertz high-pass, 10 Hertz low-pass? Who knows? Actually, just as a hint, they did something like that in that 2018 paper, so you might want to have a look. Also, there is different optimizers you can choose from. Again, I prepared a link for you that points you to the PyTorch documentation, and since my computer crashed, I don't have that link anymore, but I'm going to show you, I'm going to share it with you later on. So in this example here, we are using the, and Hubert, please correct me if I'm wrong, the ADAM optimizer. I cannot find it right now here, but there is also other ways, other optimizers. So maybe you can either pick a different optimizer, or you can change some parameters you pass to ADAM. And lastly, there's different loss functions available. Again, I will share the link with you later. Yeah, so maybe different loss functions have different outcomes, etc. So there's lots of things to explore. And yeah, if you have any questions, please do not hesitate to ask. I hope you are not totally confused now. And I hope the Colab notebook works for everyone. And yeah, I guess that's it. Let's get started.